Today's lesson is on RSA encryption. We're going to learn about two different types of encryption schemes. One is private key encryption. The example we learned about in class is a Caesar cipher. The example of a Caesar cipher is, let's say we take every letter of the alphabet and we move them down by 3. So the letter A becomes B, C, D. Okay, B becomes E, C becomes F, etc. Triple DES is the modern standard for private key encryption. That's what's used, let's say, if you're trying to make a secure connection over the internet. We also going to learn a little bit about public key encryption. The example we learned about in class is RSA. In 315 and 232, you worked a little bit with RSA. RSA has a pair of keys. One is public and one is private. In the real world, we use RSA. Okay, initially, RSA is used just to share the signed certificate so we can verify that Amazon is who they say they are. And we also use RSA to transmit a shared triple DES key, okay, for for the rest of our connection. Triple DES is then used for the rest of the secured connection because it's much faster to encrypt and decrypt using triple DES than it is to encrypt and decrypt using RSA. Well, the way RSA works is first we're going to start with two prime numbers, we'll say P and Q, and then we're going to have to calculate the modulus of the multiplication of N, which is P times Q. So let's say we're going to use the numbers P is 5 and Q is 7. In real life, they're going to have to use much larger numbers, but we're going to use small ones just so we understand. So we multiply 7 and 5 together, we get 35. So both our private key and our shared key are going to have the number 35 in it. Again, that 35 is shared publicly. The public key and the private key, which is the other part, we're going to get to in a little bit. Next step, we're going to subtract 1 from each of those prime numbers, 5 and 4, and then we're going to multiply those. So 5 minus 1 gives us 4, 7 minus 1 gives us 6, and we multiply 4 times 6. This gives us the product phi. Phi is equal to 24. Okay, we're going to look at all of the numbers that are one more than multiples of phi. Remember, our phi is 24. So numbers that are one more than multiples of phi are 24 plus 1 is 25, 49, 73, 97, 121, 145. All these numbers are multiples of 24, but then we add 1 to them. This is basically like what we call clock arithmetic. Every time we go around the clock, we're adding, in this case, 24. Okay, we're always ending up at, let's say, 1 o'clock if we have a 24-hour clock. So we're going to use 145, and we're going to factor 145. 145 is going to be equal to 5 times 29. So this is the last part of our key. Okay, so our first part of the key is 35.5, and the second key is 35.29. One can be public, the other's private. It really doesn't matter which one we choose to be public, which is private. Okay, but those are the keys we're going to be using, 35.5 and 35.29. Okay, those list of numbers, 24 plus 1, 48 plus 1, use remainder division, also called modulus division or clock arithmetic. In Python, we learned about modulus operator as the percent symbol. For example, 47% 4 means, well, 4 goes into 47 how many times? 4 goes into 47 11 times, right? That gives us 44, and then we have 3 left over, so we get a remainder of 3. Very often the modulus is used if we need to figure out if a number is even or not. So if we perform the function n%2, if we divide 2 into a number, if it's 0, then we know it's even, and if we get a 1, then we know it's going to be an odd number. So that's a very common use of modulus division. That doesn't really relate to RSA, just a little bit of review of modulus division, because we haven't done it since the fall. So we're going to say, for our message, we're going to send the word cat. All right, and the letter C is the third letter of the alphabet. A is the first letter of the alphabet, and T is the 20th letter of the alphabet. These dashes are not minus symbols; they're just dashes separating them. We're going to take each of those numbers and raise it to the power of the second part of our key. So, second part of our key is 5. So we're going to do 3 to the 5th power gives us 243. 1 to the 5th power gives us 1. 20 to the fifth power gives us this huge number. Was it 3,200,000? Okay. Remember, each of those three numbers are separate. Those dashes are dashes. They're not minus symbols. Next, we need to find the remainder of each of those, each number, okay, divided by the first part of the key. So we're going to take each of those numbers, 243, and we're going to divide 35 into it, and we get a modulus of that, of 33. 1 modulus 35 gives us a 1. 300 or 3,200,000 modulus 35 gives us a remainder of 20. This is our ciphertext. This is the message we're sending over the internet. We're sending 33,120, and the person on the other end is going to decrypt that, and they're going to get CAT, cat out of that